Good afternoon to you viewers and subscribers. Welcome back to another video. This is JK Engineering and Architecture coming to you again with another engineering video. So in today's video, I'm going to teach you how to design a reinforced concrete beam. And as I've said to you in subsequent videos, in order to design a beam, the engineer must contend with two different scenarios. The engineer is contend with shear, and he's also or she's also contend with bending. So you design a beam to withstand shear, and you design a beam to withstand bending. So that is why in my previous videos I have shown you how to plot the shear force diagram to determine the maximum shear, and also to plot the bending moments diagram to determine the maximum bending moments. So I want you to pay close attention to this video. So I'm going to show you how the beam is designed in terms of its loading, in terms of how we factor our loads, and in terms of how we add the self weight of the beam to the overall load to determine the maximum load that is going to be on that beam. So if you should look at my board here to the left, you will observe this beam here, and this beam carries a uniformly distributed load, a uniform distributed dead load of 1 kips per foot, and a uniform distributed live load of 2.45 kips per foot. The beam also spans 26 feet, and to the right on my board here is the beam's cross section. So this beam has a width of 24 inches and a depth of 30 inches. So there are also several parameters that I must bring to your attention in order for you to understand and to follow me doing this calculation. So in order to observe the maximum dead load and live load, so the maximum weight on the beam is going to be 1.2 times the dead load plus 1.6 times the live load. As I've said to you before, we kind of beef up our dead load and our live load to really ensure that the beam can carry what the load is going to be. So in other words, if the beam is going to carry 10 pounds, we design the beam to carry a little bit above 10 pounds, say 10.5 pounds or 11 pounds. So we do not just put the exact load weight in the calculation, we kind of beef it up to ensure that at the end of the design, the engineer can say to his client or to the architect that yes, is 90% sure or 100% sure that this beam can carry the load. So that is why we factor our load, so 1.2 dead plus 1.6 live. Also, if you should observe how we write the loads, this is 1.0 kips per foot, and this is 2.45 kips per foot. Now, one kip is equivalent to 1,000 pounds. So essentially, this beam is carrying 1,000 times 1. So this beam is carrying 1,000 pounds per foot on this beam, while this live load here is carrying 1,000 times 2.45. So that is 2,450 pounds per foot. So this beam is a very heavily loaded beam. So you imagine a beam to be carrying a dead load of 1,000 pounds per foot. So every foot along this beam is 1,000 pounds. So that is quite massive. So another parameter that I must bring to your attention is the weight of reinforced concrete. So the weight of reinforced concrete is 150 pounds per cubic feet, or 24 kilonewtons per meter cube. So those are essential parameters that you must understand before I get into the calculation. Also, before I get into the calculation, you should observe the concrete cover of the beam. So the concrete cover of the beam is going to be 2 inches, and this 2 inches is what is referred to as the effective depth. So the effective depth, so the beam has a overall depth of 30 inches, and we're going to subtract this 2 inches from the 30 inches, and that is going to equal to 28 inches. So this beam has a effective depth of 28 inches. So I'm going to go into the calculation now, so please stay tuned. The first step in the calculation is that we are going to find the self-weight of the beam. And as I've mentioned to you earlier, that the concrete, reinforced concrete, weighs 150 pounds per cubic feet. So this beam has a cross section of 24 inches by 30 inches in depth. So to calculate the self-weight of the beam, so in engineering design, even though the beam spans 26 feet, we are only going to design for 1 foot or 1 foot length. So to calculate the self-weight of this beam, the beam has 24 by 36, so that is 2 feet by 2.5 feet. So the self-weight of the beam self-weight is going to equal to 24 inches, which is 2 feet, times 30 inches, which is 2.5 feet, times 1 foot, times 150 pounds per feet cube. So when you work out this, if you should plug this in your calculator, you're going to end up with 750 pounds. So the weight of this beam, 1 foot length weight, is going to equal to 750 pounds. But because we are working in kips, and remember now, 1 kip is 1,000 pounds, so we have to convert this 750 pounds to kips. And also we are working in kip's foot, so we have to bring this 750 pounds to kip foot. So in order to do that, we should, if this is 750 pounds, we have to divide this by 1,000 times 1 foot, because we are bringing this to kips foot. So this will work out to be 0.75 kips foot. Because remember now, the weight on the beam is given in kips per foot. So we have to convert that self-weight of the beam in kips foot in order to be consistent with our units. So now that we have known the self-weight of the beam, right, we can add this self-weight of the beam to the dead load. So we know that the dead load on the beam, the dead load on the beam, the dead load is equal to 1.0 kips per foot, and the live load is equal to 2.45 kips per foot. So we can add this 0.75 kips foot to our dead load of the beam. So to factor our load now, we are going to have the weight is going to equal to 1.2 dead plus 1.6 live. Right? So this is going to equal to the weight. The ultimate weight is going to equal to 1.2 dead load. So we have the dead load is going to be 1 kip per foot plus 0.75 kip foot for the self weight of the beam. Kip per foot plus 1.6 times the live load, which is 2.45 kips per foot. And when you work this down now, so this is going to be 1.2 times 1.75 kips foot plus 1.6 bracket 2.45 kips foot. And then when you work this down now, so 1.2 times 1.75 is going to give you 2.01 kips foot plus 1.6 times 2.45, that is going to equal to 3.92 kips foot. And then when you add these two, 2.01 plus 3.92, you're going to end up with 6.02 kips per foot. So the total weight on the beam is going to equal to 6.02 kips per foot. So the total weight, let me write it here in case if it's not visibly clear on the bottom here. So our weight, our ultimate weight on the beam is going to equal to 6.02 kips foot. So now that we have calculated the total weight of the beam, the dead load plus our live load, we can now calculate the bending moments. And I've showed you in my previous calculation that there are two approaches to calculate the maximum shear force and the bending moment. You can either convert this UDLs into a point load, find the reaction, plot your shear force, and then plot your bending moments to determine the maximum bending moment. But we do not need to do that in this example because this beam is a UDL. So if it is a UDL, we can use the formula to calculate the maximum bending moment. So as in the case before, I have shown you that the formula to calculate the maximum bending moment previously. So the moment is really W L squared over 8. So we do not have to go through the rigors of plotting the shear force and the bending moments diagram. We can simply use the formula to do so since we are using a UDL as our loading on the beam. So to calculate the maximum bending moment, so we have MU, which is going to equal to W, and we just calculate W to be 6.02 hips foot times L squared, and we know that L squared is really the span of the beam, which is 26 feet. So we have 26 feet here, squared over 8. So our moment, when you plug this into in your calculator, the result is going to be 508.9 hip foot. So the maximum bending moment on our beam is going to equal to 508.9 hips foot. And you have seen in my previous examples, we have done a lot of calculation to come up with the maximum bending moment. And I did say to you that the reason you calculate the maximum bending moment is to calculate the area of steel or the amount of reinforcement that is going to be needed to go in the beam to withstand the load. So the maximum bending moment which we calculate here is going to be going into the formula to calculate the area of steel. Now, having calculated the maximum bending moments to be 589.69 hip foot, we can now work out our area of steel. So finally, I have gotten to the point in my videos to finally introduce to you why it is necessary to calculate the moment to go in our area of steel formula. So the formula to calculate the area of steel, that formula is the moment over phi Fy JD. It's the moment over phi Fy JD to calculate our area of steel, or area of reinforcement. So the AS here in the formula, as I've just mentioned, is the area of steel. This symbol here is known as phi, which is 0.9 for bending or flexure. So whenever time you're doing beam design and you hear the engineer or you hear the term referred to as flexure, it is referred to as bending. And what that means is that if you should imagine the beam as this, and the uniform distributed load is spread right across the beam like this, the beam is going to tend to bend like this, with this parabolic shape. So it's like this before, and when it is loaded, the tendency is going to be like this. As in the case when I show you how to plot the maximum or the maximum bending moments diagram. The bending moments diagram is going to look like this, if you can remember, right? So that phi 0.9 is for bending or flexure. Now Fy in your formula is the yield stress of steel, and we're using a yield stress of steel of 60,000 pounds per square inch, or 60 kips per square inch. Right? JD is known as the lever arm, and I should have shown you a diagram with that, but for time I'm just going to tell you what JD is. So JD is really 0.875D, and I've just calculated to you previously what D is. D is really the effective depth. So if we should go back to our diagram here, so the effective depth is going to be this 30 inches minus this 2 inches, which is 28 inches for our effective depth, right? So this is essentially, so JD is essentially this 0.875 times 28 inches, which is going to work out to be 24.5 inches. So JD is really 24.5 inches. So I can now move to calculate the area of steel. So the area of steel, and let me rewrite the formula for clarity. So the area of steel is AS equal to mu over phi Fy JD. So the area of steel is going to equal to mu, which is our moment, or maximum bending moment, which is going to be 589.69 kips foot. 589.69 kips foot, because the moment. Now we have to calculate, bring this kips foot to kips inch, because we are going to work out our area of steel, and you know our area of steel, we have different size of bars in inches. We have half-inch bar, we have 3/4 inch bar, we have 1 inch bar, and we have 5/8 inches bar. So we merely calculate our moment to inches. So to bring this 589.69 foot to inches, we multiply by 12. By 12, yeah, by 12 inches. So this is going to be all over 5, which is our 0.9 here, times Fy, yield stress of steel. We're going to use 60 KSI since we are working in kips. So this is going to be 60 KSI times JD, and JD we work out to be 24.5 inches. 24.5 inches. Now if you should run this in your calculator, you're going to end up with a result of 4.61 inch square. So our area of steel is 4 4.61 inch square. So we have to now choose a rebar to fill 4.61 inch square of our beam. We have steel. Over actual area of rebar. So if we have 461 here inch square, so if we should choose half inch steel, the area of half inch steel is 0.2 inch square. So if we should divide this 461 divided by 0.2, we're going to end up with 23 steel. And for our beam cross section, that is not going to be good, because we want our steel to be able to fit, that the rebars can place perfectly, that the concrete can go between the rebars. So if this is our cross section of steel here, our cross section of the beam, this is 24 inches by 30 inches, sorry. So our rebar, we cannot place 23 rebar here in the steel. So we have to try a bigger steel. So if we try, for argument's sake, number 8 steel, and number 8 steel is a 1 inch steel, so it's going to be, the area of 1 inch steel is going to be 0.79 inch square. So if we should divide this, if we should divide this 4.61 inch square by 0.79 inch square, and this is 1 inch bar, 1 inch bar. So if we should divide this, let's see how much steel we can use in this area of steel. So we have 4.61 divided by 0.79. So we have, so this we have here to be equal to 5.83. So we can round this up to 6. We can round this up to 6 rebar. So we're going to use, to reinforce this steel, to reinforce this beam, we have to use 6 1 inch bar in the tension zone. And as I've mentioned to you before, the rebar that is calculated has to go into the tension zone of your beam, because you have to remember that concrete is strong in compression but weak in tension. So we have to put our reinforcement in the tension zone to resist the tensile forces due to the weight on the beam itself. So we're going to use 6 beam here. So we're going to have 1, 2, 3, 4, 5, 6. So we're going to have 1, 2, 3, 4, 5, 6 beams. We're going to use, and these are 6 number 8 beams, number 8 bars, or 6 1 inch bar. 6 1 inch bar, or number 8 bars. So to reinforce this beam to carry the moments of 589.69 due to the 1 kips per foot dead load, and the 2.45 kips for live load plus the self weight of the beam, we are going to use 6 number 8 bars to withstand that load. So in order to go ahead with this and to be sure, there are several checks that I have to do to ensure that the beam itself is safe to execute or to carry out that impending load. So therefore, I'm going to stop this video right here now, and in the next video I'm going to carry out several checks to see if our moment is, if the capacity of this beam can withstand this moment due to the beam cross section. Because even though we have calculated 6 bars to withstand that load for this beam, we are not 100% sure until we carry out several checks. So the check, one of the checks that I'm going to carry out, we have to carry out the moment capacity of the beam to ensure that the moment capacity is greater than our 589.69 kips per foot. So we have to carry out this test. Our phi mn should be greater than or equal to mu, and mu is 589.69 kips foot. So when we calculate our moment capacity, it must be greater than our ultimate moment to ensure that the beam is safe to carry the impending loads. So that is it for this video. Make sure to join me in part 2 of this video to conclude this design. If you watch the video, please ensure to give me a like. I know this topic is not so well received by some, but if you watch the video, make sure to give me a like. Please ask me questions in the comment section, and please, I'm imploring you to watch my videos until the end. So thank you and enough respect, and I'm going to catch you in my another video of part 2 to continue with my beam design. Enough respect.